Hello everyone and welcome to part 2 of Introduction to Mixture of Experts. So yesterday we looked at the motivation of why we need mixture of experts, and our motivation came from neural scaling laws, which said that if we increase the number of parameters, then model performance improves, right? And sparse mixture of experts provided us a way of doing that efficiently. While keeping the computation low, we were able to scale up the model size. That was the motivation of mixture of experts. And what happens in mixture of expert is that so here on the left hand side you have a normal layer, right? So this is one expert. Consider this as one layer, right, or one neural network. An input X will come and we'll get an output Y, right? In mixture of expert, instead of this one layer, we replace it with n experts. So how much has the model size increased, right? Model size has increased n times, right? And when we are doing a forward pass through this mixture of expert, we will first use a gating network. The objective of this gating network is to select and assign probabilities to different experts, and we can accordingly select the expert. So here expert 2 and expert n-1 are selected, right? We pass the input X through both expert 2 and expert n-1 independently. This gating network is also giving me the probability of selecting that expert. We multiply that probability with this output, right? This multiplication is important because when we are doing backpropagation, gradient will flow from this route only and to train the gating network, right? And from this route to train the expert, right? Then we will add the two to get the output. Now, how many computations have increased on the right hand side as compared to the left hand side? What are the additional computations that we are doing? Right. So one is gating network and other is two experts. Now, assume for now that the gating is almost negligible because it's just one matrix multiplication, one with a softmax layer. So essentially our computation has gone from C to 2C plus routing computation, right? Whereas our model size has gone from M to approximately N into M, right? So we are able to increase the model size, whereas computation remains almost twice, and we can in fact reduce it to 1 as well if we choose only one expert instead of two experts, right? And how is this mixture of experts used in transformers? Well, on the left hand side you have one transformer block, right? And in a transformer based LLM you stack these transformer blocks on top of each other, right? And an input sequence X comes and then you get the output Y here, right? So what we do when we use mixture of experts as a layer is that in one specific layer, in one specific transformer block, we replace this feed forward layer, one neural network, with a mixture of expert layer, which is in blue box here, right? So in this example, we have increased the model size by approximately M2, approximately increased to 4M. And why am I saying 4M? Because model size includes self-attention as well, right? Whereas we have replicated only the experts, only the feed-forward network. This self-attention remains exactly the same. Number of parameters remain exactly the same. So, right, that's why it's approximately 4M. It's slightly less than 4M. And how has the computation increased? So, considering only computation of the MLPs, we are going from C to, in this case, where we are selecting only one expert, C, right? So it's C plus routing cost, right? Which is again negligible. So here we are able to keep computation almost similar while also increasing the model size, which and model size helps in improving the performance of the model, right? And this example is from Switch Transformer, and this is what they name as Switch Transformer, where only one expert is active. Before this, mostly people argued that we need to activate at least two experts so that there is a comparison between two experts and the router gets to learn by contrasting between the two choices for a given token, right? But they questioned it here and they simplified the architecture. And in today's work, we will, in today's lecture, we will focus mainly on switch transformers and innovations that it brought in, right? So this was, I think, switch transformer was amongst the first paper which introduced mixture of experts in transformers. Okay, so we looked at what are the pros and cons of this mixture of expert as a layer in transformers. We want pros, of course. We wanted to increase model parameters. We are able to do that. We wanted efficient pre-training. We achieved that due to conditional activation, right? Because only one expert is active. Conditionally, we are activating the neurons, and therefore we get faster inference as well. But then on the flip side, we observed that this may result in unstable training. We looked at the issue of expert collapse, where all experts may get trained to the same, may collapse to the same weights. We saw nonlinearity helps in avoiding that. But then router may collapse, which means that router simply learns to send to the same expert. So we have unnecessarily increased the model size, for which we will need more GPU, but effectively only one expert is active always, right? And see, this is one layer, right? And this layer is getting stacked on top of each other, and the router is also different in each layer. So there are different parameters for routers, right? So how many experts are there in the entire transformer? If, let us say, in this case, in one layer we get 4 experts, then how many experts are there in total? It's 4 times the number of layers, right? It's not 4, it's 4 times, let's say 32, then 4 cross 32 is the total number of experts. And how many paths exists for a token? If you have 4, let's say you are routing only to a single expert, then at every layer you have 4 choices. So how many paths can exist? How many paths a token can take from bottom to the top layer? It's 4 to the power 32, right? So there are so many choices that it has to learn essentially. What is the optimal path, right? So because both are learnable, definitely a token can get routed to different layers, different experts and different layers, right? Okay, so yeah, unstable training is the first issue that we will need to handle, and that is what we will discuss primarily today. And then there is high memory requirement, which we can't avoid, right? So let us start with our discussion on switch transformer layer. And so this switch transformer layer was again by Google Brain, and in their abstract they highlight 3 issues that they are trying to address. Complexity, they're trying to reduce the complexity of MoEs. They want to reduce the communication cost. We will see what does it mean. And they want to address the training instability of the MoEs, right? And so what is the idea behind switch transformer? What is the definition of switch transformer? They define it as an mixture of expert layer which routes only to a single expert instead of 2 experts, right? So greedy routing to only one expert. That is the definition, right? Now let's first look at some architecture details. How does it happen, and how are they training such large experts? So right on the left hand side you again have one transformer block where all the experts, this is a mixture of expert layer, and here all the experts are on the same GPU. So this is one GPU, one device. Let's not call it GPU because they were using TPUs for it. So this is device 0, and all the experts are on this layer, right? Now if you keep on increasing the number of experts, it becomes infeasible to put them all on a single device, right? So what they do is that they scale it with the number of devices. So if there are E experts, right, they will use E devices. So this is shard 1 which is on device 1, and this is on device E, right? In all the devices, this feed forward layer is different. This is an expert. All experts are divided, right? The other layers are replicated. So this attention layer and this multi-headed, they are exactly the same. You replicate the attention layers, right? And shard the experts. So this is some sort of an expert parallelism, and the policy that they are following here is that each expert will lie on a particular device, right? And of course, this will increase the communication cost as well, right? Because if a token is going to expert 1, then for the next computation we need to collect back, right? So there is all-to-all communication that is happening, right, depending upon where the input is, right? So this is a special case of model parallelism. We will look at that as well. Yeah. So now, how does their entire architecture looks like? In Switch Transformer, they do not replace all the FFNs with MoEs. Rather, they do it in alternate layers, right? So this block, for example, this has MoE. Here they have a single feed-forward network, right? And this entire block has 2 transformer blocks, and this is replicated n by 2 times to get n layers, right? Because there are 2 layers, 2 blocks in one, right? On the left hand side, we have an architecture where everything is on a single device, meaning all the experts are lying here on the single device. On the right hand side, experts are on different devices. So expert 1, expert E, right? And there is an all-to-all communication that will happen. Okay. So, right. So, let's start with the broad level results and the claims that the paper makes. We will again delve into how do they achieve that later on. This will give us the big picture, right? So this is again, what are we plotting here, right? So we saw neural scaling laws earlier. This is similar to that. On the x-axis, they are increasing the sparse model parameters, right? And on the y-axis, we have the test loss, right? Now, they are, so remember, so here at least this point is the base T5 model, which has 223 million parameters, and there is only one expert, the base case, right? The dense model. And the rightmost point here has 256 experts, right? So each token has to choose between 256 experts and each layer, in every alternate layers in their architecture, and this results in 14.7 billion model. The model size is increasing, right? However, they are ensuring that computation remains almost similar, right? And how are they doing that? So they basically have matched flops per token. What does it mean? That because each token is passing through only one expert, so number of activated neurons are almost the same. There is additional overhead communication cost, but approximately computation cost is same as we move along the line, right? So we have been able to keep the computation cost almost the same while reducing the test loss from 6 to let's say 4.8 here, right? And remember, we saw neural scaling laws, right, on the right hand side, and here also we are increasing the number of parameters, and we saw that the loss is reducing monotonically. The difference here is that here the flops were unrestricted, right? We were changing only the number of parameters, and we said that whatever it takes to train a model with that parameters, right? Whatever data it takes to achieve the best model with those parameters, right? Whatever compute it takes, we don't worry about the flops. So for example, if I take a point here versus a point here, obviously the number of flops used for training the best model are going to be different in both the cases, right? So this model with this many parameters may achieve saturation early on, may give me the best performance, whereas I may have to train this model with these many parameters for more number of flops, right? Whereas on the left hand side, we are ensuring that the flops are matched. Even though parameters are increasing, we are ensuring compute remains almost similar, and that is the whole idea of mixture of experts, right? So the journey is from this to this in this case, right? So okay, and so this is with respect to the model parameters. And now what about the sample efficiency, right? Sample efficiency is defined as, in a fixed number of steps, right? And when you process fixed number of tokens, what is the test loss or what is the performance that you are able to achieve, right? So for example, if I take a cross section here, I'm saying that we have 30,000 30k steps. We'll train every model for 30k steps, right? And we will see how the negative log perplexity changes. So we all know the concept of perplexity, right? We want, when we are training a model, we want perplexity to be low, right? And negative perplexity to be high, right? So higher the better. And here we see that, if we are, this is the base model with only one expert, and we can see that the sparse models are much more sample efficient as well, right? So given the fixed compute, we should train a sparse model, right? So although the advantage that we are getting, that the returns are diminishing as we increase the sparsity, right? So this is with 16 experts and this is with 128 expert. So the difference from 16 to 128 is less than the difference from 1 expert to 16 experts, right? So there are diminishing returns, but clearly sparsity helps, right? Now here on the x-axis we have training steps, right? Now one may ask that what about training time? Because you have overhead computations, you have routing, then because you are using expert parallelism, you need communication across experts. That also adds up to time, computation time. So here we look at the graph where on the x-axis we have training time, right? And we are plotting the perplexity as the training time increases, as the clock time increases. And with respect to the base model, right, this is base, T5 base, to achieve the same level of perplexity, right? So this is the same level of perplexity on, if I put a horizontal line, so it's 1.55 minus 1.55, right? T5 took 350 whatever unit that is, right? 350 units, whatever that unit is. Our switch base with 128 expert is able to achieve that in roughly 50 units of time, right? So there is 7x improvement in the time as well, right? So okay. Now this question was asked earlier as well, that what about comparison with a larger dense model, right? So here, for example, in expert parallel, what we are doing is that we are anyway increasing the number of resources. Yeah, we are using, instead of one GPU, we are using eGPUs, right? And how are we using these eGPUs? We are just sharding the experts only, FFN1, FFNE, right? To whereas all other parameters are repeated, right? Now, what if so there is a concept of model parallelism, right? So here the mixture of expert itself is modular, and therefore we are able to shard it, right? It has n modular components, and we are able to keep each modular component into a different device, right? Well, we can do that for a tensor as well. Let's say we have one big feed forward layer. Can I split one big feed forward layer into e devices? We have true that it is not sparse computation, so computations will increase, number of active units will be much more, that's fine, but at least we are using the same number of devices, right? So I mean, in fact, today all the models are trained using that concept, right, of parallelism, right? So they use multiple, because we cannot train on a single GPU, right? We have to train on multiple GPUs, right? So even for Roberta, which was a smaller model, we trained it on multiple GPUs, and what we did there was we used data parallelism, right? So in data parallelism, what we have is that we have different input examples, different batches. All of them will backpropagate. All of them will be used for training on different devices, right? Where on different devices model weights are replicated. And there is another paradigm which is model parallelism, which is typically used for large dense model. Let's quickly look at that, right? So that you understand, how do we train a larger model if we have multiple devices, right? So one simple is pipeline parallelism, right? In pipeline parallelism, what we do is that we shard the model layer by layer. On layer one will be on one GPU, second layer will be on another GPU, and so on and so forth, right? So this is called pipeline parallelism, where we are sharding a model layer by layer, right? And another mechanism is tensor parallelism. And again, in tensor parallelism, there are two ways. One is column wise splitting. So let us see how it works, right? So in any feed forward layer, we are typically doing matrix multiplications, right? So let us say this is what we have to do is A cross B, right? So this is, let's say, the input, and these are the weights, right? So this is how we typically do it in a non-distributed fashion. So each element here, C11 will be this A1 in A1 into this row B1, right? So this is A1 into this B1 will be C11, right? In column wise splitting, what we do is that we split this weight into two parts called by their columns, right? So half of the columns, these will be on first GPU, right? So this and A is replicated, so the data is sent to both the devices. On first device, first half of B is residing, right? Here we have the entire column B1, which we multiply with row A1 to get C11, right? And again, A1 is multiplied by B2, which is the second column of B, to get C12, right? And then on the other device, right, we have the second half of B, right? Here, so this is B3 multiplying with A1, we get C13, right? So C11 and C12 are computed on device 1, and C13 and C14 are computed on, so the A1 multiplied by B4 will give you C14. This they are computed on device 2, right? So this is one way of sharding one tensor. Similarly, there is another way which is called row wise splitting, right? So in row wise splitting, what we are doing is this. Again, this is input, and this is the weight matrix, right? We will cut this by rows, right? So on GPU 1 we have this row, right? And now to compute this, let's say this C11, what we need to do, we need to multiply this A11, A12, A14 with, let's say, B. So this is, how can I, let me go back. Okay, so this is C11 here, this is the output, right? And we are multiplying this A11, A12, A13 and A14 with, let's say, W11, W21, W31 and W41, right? So what is C11 here? C11 is A11 into W11 plus A12 into W21 plus A13 into W31 plus A14 into W41, right? So the idea in row wise splitting is that we are splitting the weight matrix by rows. So this computation, this part, which involves this multiplied with this, right, will be done on GPU 1, right? And this part will be done on GPU 2, right? And we need to add them, right? So this is true for all for all the elements in the output vector, right? For any Cij, this is true, right? So this is what happens. We have on GPU 0, we have to cut the input as well now, right? Because these two are getting multiplied with these two only. This happens on G1, this gets multiplied with this, and this gets multiplied with this, and we need to add the two. So this is the output on one GPU, and this is the output on another GPU. We add the two to get the final output, right? So this is row wise splitting, and this is also part of tensor parallelism, right? So we have looked at expert parallelism first, which we get in mixture of experts, right? Because by virtue of its modular design, we can use that. But however, even in the dense model, if a matrix is big, we can use tensor parallelism to split that into multiple GPUs, right? And train with, if you have more GPUs, then you can train a denser model as well using those, right? So that's what we do for T5 large, right? So we use model parallelism to split the model, the larger version of the model, which is 770 million on E experts, right? Notice here that number of flops will increase. This is kind of an unfair comparison because number of flops are increasing, right? Model is dense. We have to compute, even though we are sharding, we have to activate all of the shards, right? Whereas in MoE, only one of the shard was active. So flops increase, right? And if you look at the training steps, with respect to training steps, we see that we get comparable sample efficiency between of the two models. So this is the base model that we have, and this is the 64 expert version of the base model, the blue line, and this is our large model, right? So these two curves are almost close to each other, almost similar. However, still if we look at the clock time, right, there is still 2.5x speed up in the clock time with respect to the dense model, right? So there is, so I think this was the question which was asked yesterday as well, that if you are using extra resources anyway, then why not train a dense model? Why are we going to sparse model, right? So this is the answer to that. It is, while sample efficiency is almost similar, we see speed ups with respect to clock time, right, while training sparse models. And again, this is of an unfair comparison as well, because so these are not flop matched. Computations are also increasing in T5 large, right? Okay. So in the switch transformer layer, they claim that these are the things that they are addressing, right? Complexity of MoEs and communication cost. Well, both of these are addressed by a simple design choice, which is to route only to a single expert, right? So when you're routing, let's say you route to two experts which are residing on different GPUs or different devices, then to get the output for that specific token, you need to collect them, right? Because output for a token is the sum of the output of different experts, right? So then that increases the communication cost, right? So just this simple design choice reduces the communication cost, and it also reduces the complexity as well by definition, right? So yeah, stop one greedy routing, and I think they were the first one to challenge the belief that we need to route to at least two experts. Okay, so to address the training instability, they introduced multiple things, right? So first of them is differentiable load balancing loss, right? So this existed already. I mean, the work by Noam Shizer prior to this, which was using noisy top 2 routing and used mixture of experts and LSTM layers, they also had this some load balancing loss, but that was very complicated, and they simplified it, right? So intuitively, what this is doing is that it is basically changing the loss function to ensure that all experts are activated almost equally, right? So when we say that all experts are activated equally, we are not saying that, of course, for one token, one expert is getting activated, right? But when we are training, we train with a batch of tokens. Let's say we have 10,000 tokens in one batch, or 1 million tokens in one batch, let's say. What we want is that on an average, all of the experts should get activated. If there are 100 experts, then each expert should get on an average 100 tokens. There should be some uniform distribution of tokens to experts while training, right? But this will not happen automatically. I mean, routers can collapse and can always go to a state where they are routing each token to one particular expert. So to avoid that, what do we typically do, right? So the most common idea is to have an auxiliary loss term which will minimize only when this routing is uniform, right? So we need to design a loss term which will get minimized when we are routing to all the experts uniformly, right? So this is the idea, and let us see how do they do that. So these are certain terms. We have total n experts, let's say, and there is a batch B, and there are T tokens. So T, let's say, is 10,000, let's say, right? And Fi is the fraction of tokens dispatched to expert I. So what we are doing is that we are counting, right, which token is getting routed to which expert, right? And Fi is that. So let's if I draw here, okay. So let's say this is token 1 to token n, right? This is expert token 1 to token t. Sorry, we have t tokens, and expert 1 to expert n, right? Token 1 is getting routed to, let's say, expert 5, right? And in this column, we will record which all tokens are getting routed to expert 5. So let's say this token 10 also gets routed to expert 5, token 12 also gets routed to expert 5, and token T also gets routed to expert 5. So we will count all of this, right? And this count, so Fi is this sum over total number of tokens that we have T, right? So this is the fraction of tokens getting routed to expert 5, right? So F of 5 is this, right? So yeah, so this is the expression for that. Now what is Pi? Now think of Pi is the expected probability of selecting an expert I, right? So again, what we have is that for each token 1 to for a token I, right, consider an expert E here. I'm using the letter E. Routing probability will give me for this particular token I, we have P of E, let's say, given Xi, right? So this is what we get. This is probability of routing to expert E given Xi, right? And now, so this is P of E given Xi. Now if you have to compute P of E, what is P of E? This is the probability on an average, right? Expected probability of routing to Eth expert, right? So how will you do that? You have conditional probability. How will you compute this P of E? If you have P of E given Xi, right? So yeah, so we multiply it with P of Xi and take the sum, right? Where Xi has to be sampled from the entire universe, right? Now this is the exact value, right? And if you have to empirically estimate it, how do we do that? If you have to empirically estimate, so this is essentially, you can think of it as mean of this. This is the expected value with respect to some distribution of selecting the token Xi, of probability of the token Xi in the entire corpus, right? So this is nothing but expected value of P of E given X. Expectation is with respect to X is sampled from, let's say, the entire corpus, right? Now, how do we compute expectations when we cannot compute the probabilities exactly? Probability of selecting a token, let's say. What do we do? Right, so this is the exact expression of expectation, right? So if you have to empirically estimate, what we do? If you have to empirically estimate the expected value, right? So typically what we do, right? If you have to estimate the average of anything, mean of anything, right? You sample randomly, right? You take a sample and you select some IIDs, right? You select, let's say, 1,000 samples and take simple average of those 1,000, right? And here we have T samples, and you can say that we have X1 to XT, right? We have T tokens, right? So how will we compute this? What will be an empirical estimate of this? So 1 by T into, so the first sample that we are drawing is PE of X1. What is the second sample we are drawing? PE of X2, right? So till PE of XT, and 1 by T is the average, right? So whatever probabilities that we have here, right, we take an average. I mean, this is standard, right? This is what we do typically. If you cannot estimate the mean exactly, if you do not know the exact probabilities, right, then we draw a sample IID and then take the sample mean, right? So this is what we are doing. P of E is the expected probability of selecting the expert E, right? and this is, we are estimating it as an average of this column. What is this column? This first row has P of selecting E given x1 and so on and so forth, right? So again, coming back to the notation here, P of, this is the term P of I, which is the expected probability of selecting the expert I, right? And this is how it is being calculated, right? And what was Fi? Fi was the exact what decisions that those were taken in that particular MoE layer, right? Fractions of the tokens, those were actually passed on to that particular expert, right? And the loss that they define is simply a dot product of F and P, right? And we have to minimize this loss, right? So let us intuitively see why minimizing this will ensure uniform probability. So this is F1 P1 plus F2 P2 plus Fn Tn, right? Now if F1 is high, that means a lot of tokens are going to expert 1. To minimize this, what should happen? What should happen to P of I? Should reduce. So if a lot of tokens are routed to first expert, if we are minimizing this loss, what we should do is that the optimizer should reduce P of I, right? And we know that sum of these probabilities is 1, right? P1 to Pn, it sums to 1, and F also sums to 1. And if this goes low, then something has to increase, right? And optimizer, what should optimizer increase without affecting the total, without increasing the total sum? The one which has the lowest F, right? So if F1 had the highest F fraction, and let's say nth expert was the one which got the lowest number of tokens, right? So if you want to reduce this, you should take the value from here, because sum has to be 1, right? So intuitively, so where will the equilibrium lie? Equilibrium will lie when all of these Fi's are 1 by n and all of these Pi's become 1 by n, then that will be an equilibrium. Then you cannot move in any direction, right? So this is a simplified load balancing loss that they add, and the advantage is that it prevents router collapse and improves training efficiency by using all the devices equally, right? So remember, this is important, right? All our experts are on different devices. If everything is going to one expert, then some other device is idle, sitting idle, right? Okay. So another improvement that they do is selective precision. Again, I will quickly go through this because there is, these are all empirical experimentation that they did, right? But this result is very interesting. So typically when we are training these models, we train it in bfloat 16, right? So bfloat, which reduces the memory print by half. Instead of using floating point 32, we will use bfloat 16, right? But this increases instability because your errors are going to be more, right? You're doing computation in lower precision, that will increase the error. And typically, even when we are training dense network, what we do is that we do conditional sparsification or conditional sparsific quantization. This is called quantization, right? Selective quantization. That is weights will be in bfloat 16, but optimizer will be in bfloat 32 or floating point 32, right? So we keep optimizers in higher precision and weights in lower precision. Similarly, they also observed that if they use selective precision here, so what are they doing in selective precision? All the experts are in bfloat 16, but the router is in FP32. And why is that important? Because router has to decide the probability of routing, and they want to reduce the error there, right? And there is an softmax in the routing, right? So there is an exponentiation that is happening, and exponentiation is sensitive to computation errors as well, right? Difference, if the logic changes from 0.1 to 0.2, exponent will see a much, the derivative is high, right? So the output can change drastically there, right? So what they observe is that when they are training in bfloat 16 everything, the training diverged actually, right? And to converge the training, they had to use selective precision. So this was crucial, but this is again, this needs a lot of empirical experimentation and thought before you and come up with this. And how are they measuring the quality? They're measuring it with negative log probability and negative log perplexity. So basically higher is better, right? And look at the speed. There is, I mean, router is almost negligible computation cost with respect to the other computations, right? So practically the speed that they get is almost the same. Right? So they're able, this is kind of a free operation that they are getting, right? Okay. Another thing that they tried was reduced initialization scale. Again, I mean, this is again something which is empirical. There is no justification for this. Why is it happening? But this is how we typically initialize our parameters. We sample with mean 0 and with standard deviation square root of 1 by d, where d is the dimension, right? The input dimension. And they just reduced the standard deviation to 0.1, and they found that this gives us better stability of the training, right? So this also improves the model, and the training runs are also better. You can look at the standard deviation here, right? So they train the model 3 times and then they check the standard deviation across those 3 numbers, right? So here we see a lot of divergence. The quality is also low and the standard deviation is also high, whereas when you just change the initialization, standard deviation is also less, right? Which means that all the runs are almost similar, all the runs are converging. There's not much difference between different runs. Okay, so then another idea that they tried is higher regularization of experts. So again, typically there is a uniform dropout that is used, right, to regularize the model, and typically that value is 0.1, right? But then they're increasing the model size, right? MoEs is increasing the model size. So there are more chances of overfitting. Right? So this is machine learning 101, that if your model increases, then you need more regularization to avoid overfitting, right? So what they do to solve this is that they increase the expert dropout for increased regularization. So what they're increasing is number of experts only, and therefore they introduce extra dropout there and in only the experts. So right, so here the last row is where dropout everywhere else is 0.1, whereas in the expert layers the dropout is 0.4, and this is while fine-tuning, and they on different fine-tuning tasks, different benchmarks, they achieve the best performance with this configuration here, right? So yeah, these are the improvements that they made to improve the training instability, right? So to address the training instability. So the question is that on one hand we say that we want each input to be routed to only one expert, right? So remember we studied a synthetic experiment where we had data coming from 4 different clusters, right? And we said that if a data sample is coming from this specific cluster C1, it should get to classifier, so this classifier, right? And if it is coming from this cluster 2, it should be assigned to this expert 1, expert 2, and let's say if this is the decision boundary, expert 3, and similarly expert 4, right? Now here we are saying that first of all, here we are routing each input x. So input is a vector only to the entire model, and we are routing each input to one of the experts. On one hand, we are saying that this distribution should be skewed, right? Right. So that means that if an input x comes to a router, right? Let's say input x1 comes to a router, the distribution should be, let's say, like this. It goes to expert 1, right? If an input x2 comes to a router, this should also be skewed. It should go to expert 3, right? Now if I take all the inputs together, let's say I have x 10,000, it goes to the router, and for this also I expect it should go to a specific expert, which is, let's say, expert 2. For each input I want this to be skewed. Now from this entire data, if I compute what is the probability of selecting an expert 1, if I select an input randomly from the universe of 10,000 inputs, what is the probability of selecting an expert 1? How will you compute this? And let us say we had this 10,000 here, we had 2500 from this, we had 2500 from this, 2500 samples from this, and 2500 samples from this, right? And let us assume that the router is perfect. It is routing the samples from this cluster to expert 1 only, right? So what should be the probability for expert 1? What is the probability? If I look at it collectively, what should be the probability of expert 1? 1 by 4. What should be the probability of expert 2? 1 by 4. So there is uniformity here at the bigger picture for the when we look at the entire data together. Whereas for each token, we want it to be as skewed as possible, right? So this is the idea of load balancing loss. We are applying it on the entire batch, which is a subsample of the entire corpus, right? We cannot do it for the entire corpus of tokens. We have to do it at the batch level, right? Okay, good. So let's continue. Where were we? Yeah. Okay. So we looked at the distributed implementation of switch transformer, right? So each expert is on different GPUs, right? So typically, so these guys are from Google and they trained it on TPUs using mesh TensorFlow. And what is the advantage there? It facilitates efficient model parallel architectures, but there is a disadvantage as well, which is that the entire computation graph is static, right? So typically when you are coding, let's say in PyTorch, right, you have a weight matrix, right? It gets multiplied with some input x1, right? And you get the output y1, right? So when you are compiling, in PyTorch, when you code, you create a layer which will correspond to this W weight matrix, right? And when you are actually using this, what you do is you create a batch of inputs x1 to xt. Let's say there are t tokens in the batch, right? This is one batch, and then you are doing this W into the entire batch, right? This is batch operation, and you get all the outputs y1 to yt simultaneously, right? In PyTorch, this batch can be of dynamic size. You can have one batch which is of 10,000 tokens, and in the other batch you can have 500 tokens as well, right? So this is called dynamic, so because it creates a dynamic computational graph, right? Whereas TensorFlow, what it does is that it creates the entire computation graph is pre-compiled, meaning that you have to specify that if I have a weight matrix W, what is the batch size that you are going to use for with this weight matrix, right? So this batch size T, number of tokens in the batch size, has to be predefined, right? Now, do you see an issue when we are using mixture of experts in this specific case? So the issue is that we cannot ensure uniform distribution of tokens, right, to different experts. It may happen that let's say my batch size is 10,000, right, and I have to predefine how many tokens can an expert take, right? Let's say I have expert 1 till expert 1000, there are 1000 experts, right? So uniform distribution would mean 10 tokens x1 to x10 here, right? So 10 tokens to each expert. We have to a priori fix this, right? Let us say we fix that, right? So we fix 10 tokens will go to each expert, but then what if x1, x2 and x20 till let's say first 20 tokens, all of them gets routed to expert 1? What will happen? How will we compute that, right? So this is a practical issue, right? So here we have already introduced some terms. This 10 is called the capacity factor. What is the capacity that we are giving, that we are freezing for each expert? How many tokens can it process, right? But the question is, how do you set the capacity factor, right? Here when I'm assuming uniform distribution and I'm setting the capacity factor as, I'm distributing the batch size uniformly, right? So this is called capacity factor of 1. So this is with capacity factor of 1, right? If I keep some buffer, let's say I say that each expert can take not 10 but 15 tokens, right? So each expert W1 can get, I will reserve space for, let's say, x1 till x15, right? So this is capacity factor 1.5, right? Capacity factor 1 is essentially when I distribute the entire batch of 10,000 tokens uniformly amongst all the experts. That is capacity factor 1, and I keep the batch size of each expert as that. That is, I have to freeze that, right? I have to freeze the computation graph. So I'm allowing only those many tokens to be processed by each expert, right? So yeah, so expert capacity is tokens per batch, which was T, and number of experts is E. So in our earlier example, we had 10,000 tokens and we had 1,000 experts, right? So we had expert capacity of 10, right? So this is uniform distribution. If you do this, and then we introduce another parameter which is capacity factor, right? So when I'm in the earlier case, if we keep, instead of 10, this is capacity factor 1. If I keep 15, that is capacity factor 1.5, right? So this is how expert capacity is calculated. And so this is a schematic diagram for this. And here, in this diagram, we are assuming that the batch size is 6. There are 6 tokens, right? And these arrows are telling you the router, the expert which router selects, right? So in this case, this token gets routed to expert 1 here. This token also gets routed to expert 1, right? Now this token is also getting routed to expert 1, but we can't do anything about it, right? So this is called token dropping, right? And there is another issue here, which is this expert is now empty because we have assumed uniform distribution. If there is an overflow somewhere, there is going to be underflow in some other expert. So this is wasted capacity, and this is the dropped token. Okay. Now if I increase capacity factor to 1.5, right? Now that means earlier for 6 tokens on 3 devices, I was distributing uniformly. I was keeping capacity as 2, right? Expert capacity as 2 with capacity factor 1. With 1.5, I increase it to 3 tokens, right? Now here, token is not getting dropped. This token which was getting dropped earlier, we have a capacity for this, right? But then there are 3 slots wasted now, right? Of course, there are going to be wastage in this case, right? So now, what is the routing strategy that you should follow, right? So interestingly they observe that you should drop the token. You should not try to fix it in some other place, right? So they devise a strategy called no token left behind, which is a 2-stage routing. In stage 1, you route to the highest probability expert. You route every token to the highest probability expert, right? And if that particular expert is full already, so for example, here it is, when you are routing this, it is full. It is not able to route, right? In stage 2, what you do is that you see the second best expert which the router assigned to this particular token, right? So let's say this expert 1 was has probability P of E1 here was, let's say, 0.5, right? But it could not get selected here. Then we see what is the second best. Let's say that was expert 2 with probability 0.3. So you route this to expert 2, right? And you can iteratively do this till you have placed every token, right? So, but they stop at stage 2, and interestingly they observe that it doesn't work empirically, right? Now again, we can hypothesize why it is not working, but there is no solid theoretical proof in such cases, right? So intuitively the idea is that when you're dropping the token, it is kind of a dropout, right? And it is helping the model regularize better. This is one hypothesis that they provide, that why it doesn't work, right? So yeah, and then here they are benchmarking this versus mixture of experts. So I'm using noisy top 2 for mixture of experts because this is what existed before switch transformer came, right? So in this table they are comparing against mixture of experts. Let's skip this for now, and here they show that when you have capacity factor of 2, right? When you have capacity factor of 2, that is kind of uniform capacity for MoE base, because capacity there you're routing to 2 routers, right? Whereas in switch base there's gonna be empty slot, even if there is uniform distribution, right? And interestingly, they observe that in this case MoE is better because there is better utilization of the space, and in switch base a lot of slots are empty. Now reducing the capacity factor helps, so it's kind of maybe introducing more regularization, and therefore they see when they reduce the capacity factor to 1.25, their quality, which they measure as negative log perplexity after 100,000 steps, this setup achieves the best capacity factor, and it also improves the time to quality threshold. So this column is essentially what they are measuring here is that they want to achieve a perplexity of 1.5 whatever time it takes, right, to achieve that. So base model is not able to achieve this, and time to this quality threshold of negative 1.5 perplexity, it reaches in 65 hours, right? And yeah, so let's skip this. Okay, so here we end the discussion on switch transformers, and now let's very quickly within 5-10 minutes we will focus on mixture of experts, because this created actual buzz in the market, right? Again, I'm highlighting the important points in the abstract. They introduce an 8x7 billion model, right? So they first created a 7 billion dense model, which is called Mixtral 7 billion, right? And they created a corresponding mixture of expert model where they had this replicated 8 times, right? So what should be the size of this if this is 7 billion, and what should be the size of 8x7 billion? 56. Okay, but remember that there are other layers as well which are shared, right? You're replicating 8 times only the feed forward layer, right? Attention layers are exactly the same, right? So that's not 56, that's 47 billion. Size is 47 billion model, right? But the whole idea of sparsity is adaptive computation, reducing the computational footsteps. The number of active parameters at any point in time are only 13 billion, right? It's not even though we have been able to increase the model size to 47 billion, we activate only 13 billion, and that's what gives us faster computation, right? So this is this table is from their paper only, and they are choosing top 2 routing. So I want you to focus on these numbers, these hyperparameters. They have 32 layers of transformer blocks, and unlike switch transformer, they have 8 experts in every layer. Switch transformer had it in alternate layers, right? They are using top 2 experts instead of top 1, right? Switch was greedy, they are using 2, and they have 8 experts. And this is how their router looks like. They do not have noisy top K gating. This is simple, right, linear layer, and top K ensures that only 2 K is 2, so only 2 logits are non-zero, and then they do a softmax over it. Their final output is, so here they are using an interesting layer which is Swigglue. Instead of a linear layer, they're using linear layer with nonlinear activation. They're using a Swigglue layer. This Swigglue layer is a combination of 2 things: swish activation and gated linear units, right? So what is it? So this essentially, it has an inbuilt gating mechanism, right? So for example, look at this. So this is the input X, right? This operation sigmoid beta times X is computing the probability of choosing the input only. So it's like this. So there is some transformation that is happening, which is WX plus B, right? And input X is going here. Now they have a sigmoid here gate, this is the gate, x goes to the gate and gives me the sigmoid of beta times x. This gives me the probability of selecting, of using x, right? So with this probability, x is getting chosen, and with probability 1 minus sigmoid of beta times x, the output, this output y is getting chosen, right? So this is Swigglue layer, and people found that this is better than using simple feed forward layer, right? So again, there is a gate, there is an inherent gating mechanism here. Gating is between whether we want to do the transformation or not, right? If this sigmoid is 1, that means, I mean, we are not doing any transformation in the router, right? Okay, so right, so now the paper, is very short. Unlike Switch Transformer, this is only 8 to 13 pages paper, and they report some interesting studies on the analysis, right? They're trying to see what is actually going on underneath, right? So one hypothesis is, in general, this hypothesis is true, that the feed forward layer store domain knowledge, and the attention layer store the reasoning and the algorithms part of the transformer architecture, right? So again, this is a hypothesis. No one can prove it theoretically, right? And to test this hypothesis, what they are doing is that they are comparing Mixtral, which is dense, this Mixtral, this is the dense model, dense 7 billion, with the sparse, its corresponding sparse counterpart, right? In the sparse counterpart, we have increased the number of parameters in the feed forward layer, but we are keeping the activation almost similar, right? Computation almost similar. And on the knowledge intensive task, they find that indeed the gap between these two is actually huge, right? So this is the gap between these two, right? Whereas on the other reasoning and comprehension tasks, the gap is not much here, right? So again, they are just trying to empirically see if this hypothesis that parameters in the feed forward layer store knowledge is true or not. Right? So this is one experiment that they did, and now they are also trying to interpret the routing decisions, right? So typically, attention provides a window into the interpretation of the model, right? So what we do, when we are predicting a token, we try to see, so let's say this is the input sequence X, and we are predicting this token, right? When we compute its self-attention, we try to see where all is it attending, right? And we try to interpret that maybe, it is focusing on this part of the input to predict this, whether it is right or wrong, right? So this gives us some intuition about the interpretability of the model. Now we have a router which is choosing an expert, right? Now, can that also act as a tool for interpretation, right? To see, which token is getting routed to which expert. Is it true that all the tokens corresponding to, let's say, mathematical operations or numbers, they are getting routed to a specific expert? Is there any specialization that is happening on the expert sides, right? So this is the graph that they have. The data set that they are using here is the validation split of pile data set, which they are using for training as well. So this pile data set has a lot of, it's a collection of various data sets, right? So these are the different data sets that it has. And what they're doing is that they, at layer 0, right, they are seeing, so these are different experts, right? So for the first expert, let's say, they are seeing that if a token which belongs to archive data set versus a token that belongs to mathematics data set, right? So this red is the archive and yellow is the mathematics data set, right? Is there any difference between their distribution, right? So this horizontal line is actually the uniform distribution of 1 by 8, right? So in layer 0, we see that, there is not much difference. All this routing probability is almost uniform, right? Whereas in the middle layer, where we expect that there is some semantic thing going on, right? We see that this expert 3, right? A lot of mathematics related tokens are getting routed to this expert. So maybe this expert is focusing on, can we say that this expert is focusing on mathematics related tasks, right? I don't know. I mean, this is just one study that they're doing. I don't know whether we can say that or not. But definitely, this distribution is not uniform. Definitely, if a token is coming from archive dataset, it is not getting routed to expert 3, right, in this layer. And then there's another study which they do that, is there any relationship between routing of two consecutive tokens? If a particular token is getting routed to an expert I, then what about the next token? Is it also getting routed to the same expert I? And again, they find that in layer 0, they are closer to uniform. Uniform is 12.5, right? Whereas in layer 15, it is not uniform. It is actually very far from uniform. So that means that there is some relationship, right? There is some contiguity. If a particular token is getting routed to one expert, then its neighbor, likelihood of its neighbor getting routed to that is also high, right? And this is the final analysis that they show that which experts are active for different types of tokens. So they have 3 examples from 3 different data sets. One is coding question answer, the second is from an arithmetic question, and then MCQ question, right? And each color here depicts a different expert, right? And the only observation that they make is that, for example, these digits are getting routed to the same expert, right? Again, I don't know how to read this, right? So this again was something which was put on Twitter. What someone found was that, so what they're doing is that they're trying to figure out how much an expert is important, right? So what they're doing is that they're dropping an expert and then trying to see how the performance on a specific task on MMLU changes, right? And they see that if they drop expert 3, right, then the performance drops to 0. It's 65% here, and this is 0.63%, right? And then this was the meme which was circulated, that all the experts are just sitting idle and expert 3 is the one which is working hard, right? Maybe I can do a quick recap of what we actually did study in this, right? So first we motivated mixture of experts. Our motivation was that was coming from neural scaling laws, that as we increase the model size, model parameters, training test loss reduces, performance improves. But then we saw that it becomes infeasible to train dense large models, and we were asking the question that is there a possibility of increasing the model size while keeping the computations limited? And then we proposed sparse mixture of experts for that. What does that essentially mean? That for one layer, for one feed-forward layer, we will have n experts or n feed-forward layers. So we increase the model size by n, but when we are actually doing the forward pass, we will not pass it through all the experts, but we will activate only one of the expert, right? So total number of computation remains same, and this gives us the benefit, right? Then we looked at some synthetic experiments where we were trying to see what is, how is it learning? Why are the experts not collapsing, right? And there we found that non-linearity helps, right? If we have linear experts, then the loss function is convex, and all the experts, even though initialized differently, may collapse to the same minima, right? Whereas if you have non-linearity, then even if you're starting from similar points, non-linearity will help them to diverge, right? Then we saw that how is router getting trained, and there we saw that there are 2 stages of learning. One was the exploration stage, right, where it was assigning almost uniform probability. Router was assigning almost uniform probability to all experts. We are measuring it with entropy. Intuitive idea of entropy is that entropy is highest for uniform distribution and lowest for skewed distribution. So in the beginning, we see that the entropy was quite high. This is the exploration stage where router has not learned much, but experts are diverging. And once experts have diverged, then entropy reduces. That means now router is learning. It is learning to route to the right expert, right? And then so after this, we in today's lecture we looked at what are the issues while training a sparse mixture of experts. Those are mostly related to training instabilities, and we saw what Switch Transformers paper proposed to address those training instabilities, right? Then we also looked at how are we achieving this tremendous increase in the model size, right? Because it's not feasible to put all the model weights on one expert, so on one GPU or one device. So we saw the concept of expert parallelism, where we use as many devices as the number of experts and put each expert on a different GPU. And then we also compared it with its corresponding dense model, where we used model parallelism to split a larger dense model. And we saw that even then, switch transformers have saves a lot of time. Even though sampling efficiency is same, we save a lot of time. We saw 2.5x speed up, right? And then we looked at a mixture of experts, the latest paper that is out there, and what are the different analyses and what is the performance that it achieves. So yeah, that's it from my side. Thank you.